This is a helpful video for Newman projections, showing how we can look at organic molecules in a different kind of perspective. These can be extremely tricky, and it's important to understand how we approach them and what all the parts are representing. So let's get going on some examples. Okay, so for each of these, what we're supposed to be doing is we're going to draw the best and the worst Newman projections relative to the bond indicated. So let's bring this up here. So butane relative to the C2C3 bond. Okay, so if you think butane, what you're thinking is it might look like that, or it might look like something like this. And those are all my H's. Right? And the bond that we're looking at is that bond. So what we want to be doing is looking down that bond. So we're looking at these two carbons and what's attached to those two carbons. Well, what is attached to those two carbons? Well, there's an H, there's another H, and then there's a CH3, but that looks complicated like that. So let's redraw this one more time. And let's try to draw this in a different way. If I were to color code this, this first carbon has, or the second carbon has an H and an H bonded to a CH3. The second carbon has the same concept. Got my H, and my CH3. And what I'm doing is I'm focusing on this bond. So we're going to look at the molecule, the compound, from the end of the C. Now remember, this is still zigzag, but it's more like this. So this is the bond I'm looking at. And I'm looking at this C, the red one, and I'm looking at the blue one. But I'm going to look at it like I can rotate it, and I'm looking at the red one in front and the blue one in the back. So let's first put the back atom on. So what we do is we draw a circle. And look at what's present. I have 1, 2 H's, and a CH3. It doesn't really matter the order, but I'm going to say CH3. I'm going to say an H, and I'm going to say another H. So that is my blue carbon. That is the back carbon. The front carbon, I'm going to represent with a dot. And now what do I have? I have an H and a CH3. Okay, so I could put a CH3 here. I'm going to put an H here. I'm going to put an H here. So this would be considered staggered. And in fact, because of the CH3s are as far apart as possible, not only is this the best, but this is what we call anti. Okay, what's the worst? Eclipses are the worst. So what that would mean is that my front atom will rotate, or my back, and we will be blocking the compounds. So let's just draw. The best way to do this usually is to redraw the back atom exactly the same way. Now technically, my CH3 from this side, right, from this one, is going to be directly in front, but we can't see that. So I'm going to shift that just a little bit to the side. So if I shift that one, I'm going to shift this H, and I'm going to shift this H. And then what I'm going to do is I'm going to stagger it just a little bit. All right, this is the worst. Now, why is it the worst? Because you are causing torsional strain, because bonds are too close. But because of the CH3, it's larger than an H. This is called a total eclipse. So that is the worst. And that's how you would do that first compound. All right, let's move on. The C1-C2 bond. Again, to me, it is very important to be drawing these out first. So 1-chloropropane. All right, so what we need to do is think about what we're seeing. A propane would have 3 carbons, right? 3 carbons. So that first carbon has a Cl on it. It doesn't matter where you put it. an H, and another H. That second carbon is the carbon we're looking at, so I'm going to change the color. That's CH2, and then there's a third carbon. And instead of having this all separated, which I could do this, all my H's, but I am focusing on a different bond. I'm just going to call this CH3. Okay, so this is the bond that I'm focusing on. It's C1C2. So again, let's say the blue is the back. I'm going to have to draw this a little smaller. So if the blue is the back, look what's present. I have two H's and a CH3. What's in the front? I have a carbon, and I'm supposed to do the best versus the worst. So anything that's not a hydrogen is always going to be larger. So let's put the Cl as far away as possible, and let's do a staggered formation. So again, this is my best, the least strain. What's the worst? Some sort of an eclipse. So again, repeat the back, and pause if you need to, and take a look at my staggered and my eclipse drawings and my Newman projections based on my Lewis structures, how I have them color-coded. Doesn't matter which side I put them on, as long as I'm staggering it, or putting it to the side to make an eclipse. And that would be my worst. So that's how that one would look like. Let's look at the C2-C3 bond of our next compound. So this is 2-methylbutane. Okay, so we're adding something each time. So 2-methyl means it's the second carbon where there's a methyl group. Okay, so there's a methyl group there. What else would be on that carbon? Well, there'd be an H to give it the 4 bonds. Okay, the rest of that compound, if it's butane, would have a C and then another C. There's my 4 C's right there, right? Butane, 4 carbons. All right, but what are on those carbons? Well, those would be H's. And then this last carbon would have 3 more H's. But why am I not drawing them out? Because I'm focusing on this bond. So same idea here is that C is not the bond I'm looking at. So I keep everything else together. So coming back over to my Newman projections, I'm going to do the back one first. So I'm going to try to stay consistent here. So there is my back atom. And my front atom is going to be a little different. And there's multiple ways that I could do this. So what do I have? I have 2 CH3s. So maybe I could put a CH3 here. And maybe I could put another CH3 down here. Now I'll talk about why I'm doing this first. So that's one way. But that's not the only choice I could have made. I could have made this as well. Repeat the back. I could have also done it like this. You don't necessarily have to come up with both, but I want to talk about why. All right, these are the best, but they are not great, but they are better than nothing. So basically, these equal each other. But what we have going on here, which we're going to label more and more and more, is there's a goosh right here between compounds, and there's a goosh right here. So there's a one goosh. There's a one goosh Newman projection. It's not a anti. You can't get it as far away as possible. This one's as far away as that methyl group, but this methyl group is not does not have an option. Okay, but if I put both CH3s here and here, then I'd have 2 gooshes, meaning 2 compounds or branches that are close to each other, and that would put on additional strain. So my best structure is when I can limit the number of gooshes. Okay, what would be the worst? Well, when you are eclipsing your CH3s in front of your other CH3s. So we could do this multiple ways. I'm only going to draw one just for the sake of room. So if I put a CH3 right here, as long as I place the CH3 anywhere else, so I could have it in front of this H, and then this one could be here. What would be the other way? You could have the methyl group on the lower right H. instead. So this would be the worst. So that's examples of the best and the worst for that one. Okay, we're going to continually get more complicated. So here we go. What if I do the C2C3 bond on 2,2-dimethylbutane? Okay, it's getting more complicated. Break it down. Again, you're going to have 4 carbons. So the reason why I'm writing it like this in the beginning is just to show you again what I'm trying to break this apart. I want that bond, right? So that's why I'm breaking that apart. So all the red needs to be the red parts of my Newman structure projection, and my blue needs to be the back part of my Newman projection. So let's take a look. 2,2-dimethyl means that I would have 2 methyl groups here. And then, in this case, this last one still has to be there. That's going to be another methyl group. And the reason why it's not a methyl group, but it's part of the chain. The other part, that will be H's. And this will be CH3. So there's 3 parts. You're always wanting 3 bonds. That's kind of the goal, right? 3 bonds. So if you can kind of see that, I have 3 bonds here. I have 3 bonds there coming off of my carbons. All right, let's go to the Newman projections. I'm going to bring this down a little bit here. So the back one, I'm going to make this a little smaller again. Very consistent. Nothing's really changed with the back one. We're kind of focusing more on what happens to the front. So what's happening with the front? I have all methyls. So there's really no options. The best way would be staggered. And what would be the worst? Well, an eclipse. Still would look the same. Well, let's make that blue. And then all I do is I write it to the side. And that would be my worst. And this is my best. Now, if you were asked what's going on, and are there any conditions here, I have 2 gouaches here. There's 2 gouaches. Okay, here on the other one, I have an actual eclipse going on. So that's how that one works. All right, let's do one more. And this one adds to what's kind of happening to the overall Newman projection. So this is pentane, but I want still the second to third bond. So I'll try to keep this color-coded as much as possible. There's the first 2. I'm going to go to the third bond, the third carbon. So then there's a C and another C, right? Well, let's take a look at what this means. So it says 2-chloro. So there's where the Cl. It says 2-methyl. So there's a methyl there. This is the ending, so that would just need 3 more H's. So there's my 3 bonds. Okay, how do I get 3 bonds out of that third carbon, though? Here's the trick. Well, you got to be smart about it and think I need 3 bonds here. So there's 1 for my H, there's 2, and there's 3. So this part right here, I need to keep all together. I can't break this apart. So think about what's there. Instead of doing this with H's, what I'm going to do is simply write the H's in there. So this is going to be CH2 and CH3. Okay, what does that mean for my structure? Well, let's take a look. So if I draw the blue, hopefully this will make some sense, is I have an H here, just like we had before, but now I have a C2H3. I have an ethyl group. That's all. I just have an ethyl group. All right. If I want to make this as the best I possibly can, then what I need is I need to at least place, check this out, Cl is smaller than methyl. All right, you don't want the largest components to be next to each other. So by putting Cl here and CH is here, what I've done is I've placed my larger structures closer to the other large structure. So the best structure would be at least a Cl being close to that ethyl group. So it could go here or it could go here. It really doesn't matter at all. So I'm just going to place it right here. And then I need to place the other methyls in a staggered formation. So that would be my best. And again, I could put the chlorine on the other side as well. So I could draw this twice. And on the answer key, I did draw it twice. Whoops, that's the best. The worst, let's finish this up. I just redraw the blue the exact same way. It's easier. It's much more consistent. The worst would be, as I stated in the beginning, is that you're going to have to do eclipse. But then not only would you want to do eclipse, but the one that is not going to eclipse the ethyl is the chlorine. So as long as you're putting the CH3 right here, you could put the chlorine here, or you could put the chlorine here. It doesn't matter. It does not matter. Let's just put it here. And then let's put the CH3 right here. So you could have two of these structures. And that would be the worst. Okay. So that's how that kind of works. Let's talk about rotation barrier. Rotation barrier is interesting because it's the difference between the best and the worst. So how you figure this out is if you can figure out what the worst looks like, the worst structure would kind of give you a hint on the biggest jump. So let me give you an example. When you look at this first one, way to the right, again, you need to kind of use the codes here. ET means ethyl. IPR means isopropyl. Okay? So if you have this bond right here, think of this as a carbon, and there's another carbon. Okay? If you had it like that, then let's actually color code this. Let's say this is the back, and this is the front. Let's talk about what's on there. Okay? So if I draw this, let's do the blue. Okay, what do I have? I have an IPR. Okay? I have an ethyl group. And what do you think is left? If that's a carbon, what else is needed? I need an H. Right? You need 3 bonds. Where's that 4th bond? It's going straight in the middle. It's right here. It's going right down the center. All right, but we're going to call that red. Okay, so now what is going on there? Well, I have an ET. I have an ET, and then what's the third one? Another hydrogen. But this is not the way I want to draw this. I really haven't thought this through. I need to think about this in the worst conditions. So the worst conditions would be an eclipse. And specifically, how would I want to do that? If I would bring that around, I would want the largest things in front of other larger ones. So if I put an ET in front of an H, that's not the biggest strain or resistance. So what I want to do is I want to make sure that I'm placing an ET in front of the isopropyl and another ET in front of the other ethyl. And then the last one, I'll just put an H in front of that. So this is the worst. So let's talk about what's happening here. I have a total eclipse is when you have large structures. So right here and right here, I have 2 total eclipses. That's pretty bad. That's pretty bad. So I'm going to quickly draw these other ones right here. So again, I think what helps is imagining this. So this is a carbon. I do each one of these exactly the same way. And that's a carbon. And then you got to imagine, okay, so I have an H and another H. I have a H and another H. So this would look like this. That would be that carbon. Oops. Let's fix that. And then again, how do I want to make this bad? I'm going to put an ET in front with my other H's. So what do I have? I have 1. I have 1 eclipse, 1 total eclipse. Okay? I'm going to keep moving here. Okay, again, we're going to make it as bad as possible, so giving it the most strain. By making it the worst possible, then the difference between its best staggered and its worst eclipse will be the largest rotation barrier. So here I have another total eclipse, but this is different. This is larger than that ET, right? So this is a worse eclipse. So right now, if I were going to rank just these, this would be the largest rotation barrier. This would be the second, and this would be the third, because although this looks like it ties because you each have 1 total eclipse, The one on the left is worse because of the size. Okay, finishing this off. So here, what do you have here? Well, this is CH3. This is an H and an H. This is CH3 at the end, and this is an H and an H. So bringing this down right here, I have same concepts. Okay, so again, look, I have a total eclipse, but methyls are smaller than an ethyl. So this is probably 4, I'm going to guess. This one would look like this. Says it right here, halogens are smaller than methyls. So this is even smaller than the previous problem. So this is 5. And then this final one right here is if I just have carbon. This is just carbon right here. So I just have 3 H's right here. H's are nothing. It would look like this. And then my front one, wherever I want to put it, would have 1 CH3 and H's. Well, why? Because if this is a carbon, that's CH3 and then HH. So this would be the worst because it has the least amount of strain. So that's how that would work out. All right, so let's take a look at the next page, which is kind of discussing what is causing strain. And for you, I think what's going to help is that maybe you can process this as the greater the strain, the more unstable and unlikely this is going to occur. Okay, so what it's asking is, what's the difference why the first one is so much more stable than the second one? Why is this greater? Why is this better? Why is this one better than the second one? Okay, why is this the best and this is so much worse? Okay, so what we do on this one is that first problem that is definitely perfect. It's an anti, actually. It's as far apart as possible, so we are not getting any strain there at all. But on this one, it is still staggered. These are both staggered. Staggered is good. Eclipse is when something's covering another one up. But right here is what we call a gouche. Okay, and a gouche is when there are atoms that are too close. So when atoms are too close, it's considered a steric strain. So we're going to actually say that there's one gouche. I think that helps a lot in thinking about that. So I'm going to label it every time with a line in between the gouches. So there's one gouche so that it creates a little bit of strain, but they are both staggered. They are both staggered. That's good. So there isn't nearly as much strain. They are both staggered. All right, let's take a look at the next one. This first one is staggered. Right, second one is an eclipse. Okay, there's a big difference with those. When you have a staggered versus an eclipse, that is called a torsional strain. That's the difference between them. That's why there's so much energy in between. If you move the first one and then you rotate it into the second position. Just imagine that. We are rotating the first one into the second one. So the first one is staggered, the second one is eclipse. When you move from staggered to eclipse, that is called torsional. Okay, take a look at the number 9. This is, again, staggered. Okay, this is definitely an eclipse. Okay, but there's extra things going on here because you also have this atom-atom strain. Right? You have atoms too close together. That's called a total eclipse. So what you have is you're going to have torsional, and the reason why is that you're going from staggered to eclipse. But because you have a total eclipse and you have those compounds, those branches that are larger than H, you're going to, hydrogen, you're going to have a steric strain as well. Okay, let's look at number 10. Number 10, the first one, it's all staggered and just hydrogens. Really nothing's going on there. And then here, we just twist it. So because, again, you went from staggered to eclipse and nothing else happened, this is the classic definition of a torsional. There's really nothing else to say about that one. staggered versus eclipsed. Okay, this next one, reminder that IPR is a isopropyl, so it's a pretty large structure. So they are both staggered. They're both staggered. But why is this one better than that one? Well, the reason is that you got to look at the branches that are, again, larger than hydrogen. So in this first one, the goosh is between the CH3 and the CH3. The second one is between a CH3 and an IPR. So this is larger. So the larger the mass, the more electrons, the more repulsion. So any kind of a strain that is a result of atoms is always steric. So we just went from basically, you had the same amount of gooshes, but the larger isopropyl causes the second one to have a larger strain. Okay, the next ones are both eclipse. So then you have to think about, again, what is happening here. So you have an eclipse with a CH3 and a CH3. In this one, you have an IPR and a CH3. So what do we say? When it's between atoms, then that is going to be a steric. That's going to be a steric strain. And why is this one greater? Because, again, you're going to have a larger strain with the IPR. Okay, it's a methyl-methyl versus a methyl isopropyl. And finally, number 13, I think this is my favorite one of the 6 or 7 that we just did, is that why is the first one better than the second one? They're both staggered, so then you have to think about where things are located. Here we have 1 goosh. Here we have 2 gooshes. Okay, so what's a goosh? It's going to be a steric strain because, again, that's dealing with atoms. Okay, so you went from 1 goosh to 2. So that's going to create more strain. The final page works on Newman projection energy diagrams, and I think these truly kind of show your understanding of which projections and which formations have a lower or higher energy based on the strain that exists. And it makes you understand the difference between eclipse and staggered and the differences between those. So first off, when I just look at this, it's important to understand that when we are rotating this every 60 degrees. So I'm actually going to quickly just write down all of the degrees here. And it's all based on moving just the front atom around the back atom or the second atom in the bond that we are focusing on. It doesn't really matter what bond it is, it's the bond that we've been given. So in this case, we are between 2 carbon atoms in I believe, a 6-carbon ring or chain. So I think it's important to also recognize what's happening here in the fact that we have an eclipse, we have a staggered, an eclipse, a staggered, an eclipse, a staggered, and an eclipse. And I'm actually going to move all these up, so then these are going to be out of the way a little bit. Okay, so this one is simpler than the other 2 that we have, so it's important to kind of notice this. So I'm going to highlight a few parts to this, but there is no value here. You are just recognizing of this list, of the 7 that we're going to plot, the worst structures will have the highest, the ones that have the most strain will have the highest energy, and the best lowest strain will have the lowest energy. Okay, so if I look at the first one, this is the important part. I have a carbon, the methyl is in front of the isopropyl. That is by far going to be the worst. That's an eclipse. Eclipses are always going to be higher, and that's going to be the same here as well. So I'm going to map out that on the 360. Here, let's just do a dotted line here. And let's do a dotted line on the lowest. So those are going to be my worst. Let me change the color. That's going to be the highest energy. So the worst formation considering strain. What is the best? Well, it would be a staggered, right? And if those are the worst being in front of each other, then you'd think that being as far apart as possible would be the best. So if I look at this, that looks like that's as far away as possible. So at 180 degrees, we're going to put that as the lowest. So that's a good starting point. Okay, let's talk about the rest of these as we go. The staggered should be low, and the eclipse should be much higher. So actually, I want to just look at the staggered ones here for a second. So looking at these, check this out. You have the isopropyl and the methyl, but although they're staggered, they are close together. So what have we been talking about and learning? That's a gauche. Okay, there's some steric strain. So there is no value for this right now, but what I'm going to say is that at 60 and at 300, those are going to be a little higher than at the 180 where it's called an anti or as far apart as possible. So those gauches cause a little strain, right? Those have some gauche. So this is the anti. That's the best. And then this has a gauche, right? That matters. Okay, we have two left to place. So if we look at the 120 and the 300, I'm sorry, the 240, those are both eclipses, but notice that they are eclipses where we are not covering each other up. So think about that. Would it be all the way up here, or would it be lower? Well, it doesn't have as much strain because it's not a total eclipse. So we're going to bring it down a little bit, and we're going to make those even, though, because they have the same. So this is a total eclipse. And this is simply an eclipse. So if I map this out, then it looks something like this. And you'll notice that the anti is the lowest, the gauches are higher, the eclipses are higher yet, and then the total eclipses are the highest. So hopefully you could follow that train of thought, or else rewind this and go through it again. Let's take a look at the next situation. Two left. Again, let's. I'm just going to quickly go through this. This is 0. This is 60. This is 120. This is 180. 240. Just so we can keep track of that. Okay. And I think, again, it's silly, but I think it helps visually see this. It will always go back and forth. So take a moment. Where is the best? Where is the worst? This might look a little different than the last one, and it gets interesting as we go. So I want to find the best and worst, though. So the best and the worst ones will be the eclipses and the staggereds. The eclipses with the biggest masses in front of each other will be the worst. So again, I see a methyl group in front of each other, and then it always repeats itself. So those look like the worst. So I'm going to put those. I'm going to put those at top. Those are my worst. Are they as bad as the other ones? It doesn't matter. It's not like that's a value that I have to place. All right, where's the best one? It would be an anti where the methyl or the isopropyl or the large branches are as far apart as possible. If I look at this staggered is still the one that's furthest away. So I am saying that that's the lowest. All right, so the last one, if I just do this in red for a second, what we had it was they went right here, and then they were right here, and that was our diagram, right? So these were all even, these were even. Well, let's take a look at what we have going on this time, because this is going to be a little different. And it's not about knowing the exact value, it's a relative idea from one to the next. So we're going to break this down one at a time. So if I look at this, let's look at the number 60. Here's a staggered, but I have two gauches. Here, I have carbons in front of each other, or the methyls again. Isn't that exactly the same as that? You'd be like, yeah, it is. So I am confident in the 121. I'm not sure about the 60 yet. Let's keep going through. This eclipse, they're not by each other at all. They're all separate. Right? So the one at 240 should be lower than the ones at 0 and 120. So those are my three eclipses. Or sorry, my four eclipses. This is an eclipse, an eclipse, eclipse. So now I have some staggards to place. So let's look at the other staggered. I have one goosh. I only have one. So gooshes create more strain. So the 300 should be lower and the 60 should be higher. Right? This is more strain than this one because this has two gooshes and this only has one. It says one goosh. This has two gooshes. So there's my map right here. So that is my energy diagram for my Newman projection on that one. Because of the two gooshes versus the one goosh, I have a difference in level. Actually, and then right here as well. Okay. And again, there's other ways to do this. You could have said eclipse, staggered, eclipse, staggered, eclipse, staggered, eclipse. Notice that still the staggards are lower than the eclipses, but they change. All right, final one. So now we're dealing with multiple methyls and isopropyl. So let's do this again. I'm going to actually write it down here. Eclipse, staggered, eclipse, staggered, eclipse, staggered, eclipse. Okay. So let's take a look. You got the isopropyl in front or behind the methyl. So that's going to be the worst. Let's get some lines again. Okay, where's the best one? Unfortunately for this, you do have a goosh going on right here, but the methyl is far away as possible from the isopropyl. So that is going to be the best. And if you're thinking, but there's a goosh there, why is it as low as possible? Because on this diagram, that's as low as it's going to be. Okay, let's take a look at the other two staggards. Let's just focus on those for a second. Here, I have a goosh and another goosh. There's two gooshes there. And then my other staggered, I have a goosh. I only have one goosh. So the 300 should be lower than the 60. Right? One goosh is less strain than two gooshes. Finally, let's take a look at this. I have an eclipse with methyls, and here I have my methyls in front of H's, and nothing's in front of the IPR. Well, that's not a lot of strain. That's actually going to be quite low. So this one is going to be just a little higher than the other staggered, and then I would think that this one would be somewhere in the middle because I have that strain right here. So, oops. So my final drawing would look something like this. So each one of them is different. Each one has its own special qualities to them, but you have to start understanding the differences between eclipses, the differences between staggered, the differences between total eclipses, and the difference between gooshes on the staggered. I hope this is a helpful overview of Newman projections. We will continue to practice this and go through it additional times if you need that extra help.